Thank you very much for the kind introduction. Hello everyone. My name is Dinithi, and I'm a computational postdoc from the Wellcome Sanger Institute in the UK. And today I'm going to present the work that I did as part of my PhD at Monash University, Australia, with my PhD supervisors. You see here in this picture, Dr. Arun Konaguttu and Dr. Lloyd Addison. So in this work, we wanted to see how we can bridge the gaps between current protein alignment models. And then for that, we tried to come up with a Bayesian information theoretic framework that can actually infer an optimal alignment model, which gives us a way to connect the amino acid substitutions and insertions and deletions together consistently, as well as to evaluate any kind of substitution model in a reliable manner. So to begin with, I will give you the motivation behind this work. So as we all know, when we are comparing proteins, we usually do it via a computational technique called alignment. And in alignment, we are assigning a one-to-one correspondence between amino acids of the protein sequences. And it actually allows us to answer the question whether two or more proteins are evolutionarily related. And if so, how exactly are they related? And the usual common criteria that we use to generate an alignment has two main parts. First is a scoring scheme to quantify this evolutionary relationship, and that has to take into account an amino acid substitution matrix to quantify the matches, and then a gap penalty function to penalize the insertions and deletions. And then the second part involves a search algorithm to obtain the best optimal alignment, and this is usually done via dynamic programming approaches. So, however, in this scheme of things, we sort of know two shortcomings in the common alignment criteria we just show now. First is that these scoring functions that are being used are mainly ad hoc, and there can be arbitrary choices in the parameter configurations. And then there is also a severe disconnect between the substitution scores and gap parameters in use. And this has been actually highlighted by several notable literature that I have listed here. And specifically, we see that there is a lack of a formal and robust framework to derive evolutionary time-dependent substitution and gap models. And then there is no objective framework to evaluate any given substitution matrix. So we wanted to kind of address these two highlighted issues. And to that, we came up with a Bayesian information theoretic framework that allows us to do three key tasks. First, to infer an improved Markov model of amino acid substitution, and then to infer time parameterized three-state alignment models to accompany that Markov model. And finally, to compare any given set of existing substitution matrices in terms of the Shannon information, given any benchmark protein alignment dataset. So this framework leverages the statistical inductive inference framework known as the minimum message length inference framework. And to give you a little bit of detail about this framework, MML was introduced by an Australian computer scientist, late Professor Chris Wallace, in 1968. And this is actually a statistical inductive inference framework which allows us to do model selection. And we can have a trade-off in model fit and model complexity when we are using this framework. And it actually combines the well-known Bayes theorem with the Shannon information content. So in Bayes theorem, as you can see here, we already know that there's the joint probability of some hypothesis, and some data is defined as the product of the likelihood of that data and the prior of the hypothesis. And then separately, we have the Shannon information content, which gives us the optimal encoding length of an event as the negative log of the probability of that event. So with that, we kind of see MML as an imaginary data transmission between two parties. So suppose that there is someone who wants to send some data, and some model or hypothesis that describe those data jointly as a message in some binary transmission channel. And then this message is actually of two parts. Under the MML framework, we have the first part that has to encode the hypothesis details, and then the second part which has to encode the data given the hypothesis details. And this is a lossless compression, so all the details needed to decode this data has to be sent throughout the communication itself. And then we kind of define the total message length, and then we can expect the optimal model to actually minimize this total message length. So we can have an optimization of a model using this framework, and also it enables us to compare between different models to see how one performs over the other. So it can be done using this kind of compression statistic, where we kind of get the difference between these joint message length difference. So with that, we wanted to go into an MML framework that allows us to come up with a protein alignment model. So to describe what is the exact problem that we were trying to address here, suppose that we have a certain common alignment model H and some benchmark protein alignment data set where we have sequence pairs and their alignments. So let's say we have SI and TI as two sequences, and then we have alignment I that describes their relationship. So this is an example alignment as such. So you can see that each of these columns are over three states: matches, insertions, and deletions. And then the general, we can generally take this as a sequence generated from this kind of finite state machine. This is a symmetric machine, as you can see, where insertions and deletions are treated equivalently. And there are three free parameters involved. And I will come back to this later on in the slides. So with this set of data and the common alignment model, we kind of formulated an MML message to communicate the entire protein alignment benchmark between two parties. And so we have a first part as encoding the common model, and then second part as encoding all the protein alignments given this common model. And this is the total message length associated. I will go into each of these components. As you can see, we have the second part much more elaborated here as another MML, nested MML formulation, which I will talk about in the other slides. So the first part encodes our common alignment model parameters. So if I go to what are the elements of it, the first one is we have to encode a Markov matrix of amino acid substitutions to quantify the matches. And then we encode a null probability model P for quantifying the insertions and deletions. And then finally, we are also encoding evolutionary time parameterized pairs of Dirichlet parameter models for relating matches and indels with evolutionary divergence. I will go into each of these elements now. So if you take the Markov matrix, this is actually a 20 cross 20 transition probability matrix. And the well-known example is the historic PAM matrix by Margaret Dayhoff and the colleagues published in 1978. And this matrix allows us to define some evolutionary time unit. And typically this is taken as the point as an expected change of 0.01 in the amino acids overall. So this matrix, each column is a probability vector that sums up to 1. And then if we extrapolate this matrix to a higher power, m to the power of n, let's say, it gives us the probability of an amino acid changing into another amino acid in n time steps. And then another property of this Markov matrix is that there's a stationary distribution. So if when n is going to the infinity, that means the m is reaching the equilibrium, and therefore it gets into the stationary distribution. Where at that point we can say that the Markov matrix is no longer able to differentiate between significant amino acid substitutions and just null occurrences of amino acids. And then in this framework, we are also considering a non-Markov matrix. So if we have a non-Markov matrix, we will approximate it as a Markov matrix by taking the kth root of that matrix, which correspond to a 0.01 expected change in amino acids. So with that, to encode this matrix, we take it as a set of 20 points in a unit 19 simplex, and we simply compute the encoding length under the MML framework. The second part of this is the amino acid null probability model. It's just the 20-state probability distribution. And we can simply take the stationary distribution of the Markov matrix for this case. In that way, we don't have to really communicate, because the stationary distribution can be taken by normalizing the eigenvector, which is associated with the largest eigenvalue, which is 1 of the Markov matrix. But if we are to estimate it as a universal distribution over any kind of protein corpus, we will need to actually communicate the probability distribution. And then that is done as a point in a unit 19 simplex as well. The next is the evolutionary time parameterized Dirichlet models. So let me just describe what I meant by here. So in this finite state machine, we have 3 free parameters, one associated with the match state, and we model that parameter as a one simplex Dirichlet model. Let's say Dirichlet alpha m. Alpha m is the Dirichlet parameter. And then the rest of the two are modeled as two simplex Dirichlet model. And then we have alpha m and alpha I for each evolutionary time point, and then we take a range of time points, and then this gives us a set of parameters, Dirichlet parameters, as a function of time. And then we encode these Dirichlet model parameters again under the MML framework by assuming that the Dirichlet parameter is a product. Usually it's a product of a mean vector and a concentration parameter. So we take priors, a uniform prior and a well-behaved prior for the concentration parameter, and then we encode it. And then finally, we can compute this message length. So with that, now I will go to the second part. In the second part, it's actually where we have to encode each and every sequence pair which is aligned. So each encoding of an alignment can be taken as another MML formulation. So it's a nested MML formulation here. So first message is where we have to send the alignment information, and then we have to send the data, the sequence data, given this alignment information. So not just the alignment information. When I say alignment, it includes the alignment itself as a 3-state string, as well as the common alignment model that I just mentioned as the first part. So in this case, the first part has to encode 3 elements. First is an optimal evolutionary time parameter under the Markov model that we have, and then the optimal 3 free parameters for this state machine over the time t relevant Dirichlet models, and that is associated with this particular optimal time. And then finally, the 3-state alignment string itself. And then we have the total message length like this. The second part is quite straightforward. We are encoding all these columns according to their state. So if it is a match state, then we take these amino acid residues and encode them using the joint probability that we obtain from the Markov matrix we have under the optimal evolutionary distance. And then for insertions and deletions, we can simply take the null model and encode them. So now that we have all the parts described, we have a total message length or Shannon information content that we have defined for communicating a protein alignment benchmark. And then it allows us to compare any 2 common alignment models and see what is giving us the minimum message. With that, we can also do a search for the optimal inference, optimal parameters. And then the approach we took was a standard iterative approach, just like expectation maximization with simulated annealing. So we start with by fixing the 3-state alignment model parameters that are described by the Dirichlet parameters. And then we optimize the substitution metrics, the Markov model, and the evolutionary time associated with that. And then we fix them, and then we partition this entire data set into time bins based on their evolutionary time. And then for each time, we estimate the Dirichlet parameters again. And then we do this iteratively until convergence. So with this, we were able to actually infer Markov models across several benchmarks. And I'm very excited to share the results here. So first of all, the benchmarks that we considered were these six: the Homestrat MacBench, the SAGMark superfamily relationships, SAGMark twilight zone relationships, and then the SCOP database. And here, these are structural alignments that have been generated over a range of structural alignment programs. Specifically, for the SCOP datasets, the first version is having DALI structural alignments, and SCOP2 has Malina structural alignments. And then we also considered 9 substitution matrices, all the way starting from PAM matrix 1978, and all the rest of the matrices have been published during the last 4 decades, all the way from JTT, Blossom 62, JO, the Overington structure-based substitution matrix, the WAG, VTML, LG, MIQS, and PFSAM family. As you can see, there are Markov and non-Markov both models here. And under our framework, it is possible to convert the non-Markov matrices into their approximate form of Markov models. So with that, we got the total Shannon information for each of these substitution matrices under each of these benchmarks. So you can see that overall, there's a trend of improvement over time, which is quite nicely shown in this as a general trend, starting from PAM, which is the worst performer with the most high message length, which is obvious because at that time there was a limited protein corpus, and therefore it was on a limited data set. So, but overall, you can see that Blossom is well performing across benchmarks still, even if it is from 1992, which is quite nice observation again, because it's kind of reassuring us that the framework has been able to identify the performance of a widely used matrix series as Blossom. And then you can see that later substitution matrices are performing well than the very early substitution matrices like JO, for instance, even though if it was from structural alignment data. And so it's nice to see the trend of improvement overall in substitution modeling of efforts over time. And now that we had this, the existing substitution matrices evaluated, we wanted to evaluate our Markov models that were inferred over each benchmark as well. And then finally, we came up with a statistic to evaluate all the matrices. So the first are the 9 existing matrices, and these are the 6 MML inferred Markov matrices over each of the benchmark alignment datasets. And then we computed the rank sum statistic, which is simply the rank, the sum of the ranks of a certain model across all the benchmarks. And then we see that the best performer among all is this MML matrix estimated over the SCOP2 database. So we take it as MML sum, the MML substitution matrix. So just to give you some properties of the MML sum matrix, this is the set of 1 simplex Dirichlet models that we inferred as optimal for under the MML sum evolutionary time for the SCOP2 dataset. And then these are the 2 simplex Dirichlet models for the same evolutionary time axis. And if we can also look at the expected change in amino acids of them under the matrix, and then the probability, the average probability of going from match state to another match state, and probability of going from an insertion state to another insertion state. And all these actually highlight the fact that, highlight the point where the matrix reaching its equilibrium state as well. And that's the point where it loses the differentiability between substitutions and insertions and deletions overall. This is another set of visualizations over the matrix. We did hierarchical clustering and also some t-SNE embeddings to see if they give us some insights on the amino acid groupings based on physicochemical characteristics, and we see sensible results here as well. And then finally, we did some independent examination of the functional similarity of proteins that we had in the SCOP2 database, the SCOP2 benchmark dataset that we had. This was done by taking the gene ontology annotations of all the pairs of proteins we had there. And then we plotted it as a function of the optimal evolutionary distance under the MMSM matrix. And then you can see that we can quite nicely see, as expected, the functional similarity kinds of decreases over time, and until up to this point, and then again things get scattered a bit. This is the point actually where MML sum loses its differentiability between substitutions and indels as well. And it's nice to see that that kind of agrees, and we see the correlation between function similarity and the evolutionary distance. So finally, as a summary, we presented here an unsupervised Bayesian information theoretic framework, which actually allows us to come up with a Markov model of amino acid substitution for any given protein alignment benchmark. And then we can also infer evolutionary time parameterized tree-state alignment models to accompany this Markov model. And then finally, we can also objectively assess any amino acid substitution metrics under the framework without really having to worry about arbitrary parameter choices. So this new MMSM series is available at this link for download, and also it contains the supplementary material and the C++ code that implements this framework. You can also check out an application of MMSM from this publication, which was presented today at 3D COSI Proceedings. It's actually investigating the expected distance between sequence alignments and structure alignments as a function of evolutionary time. So with that, I would like to conclude my presentation, and I would also like to take this opportunity to thank my PhD supervisors, Dr. Arun Konabutu and Dr. Lloyd Allison, and Monash University, Australia, and also my family, my parents, my family, my friends, and everyone who supported me during my PhD journey and who made it a very wonderful journey for me. Thank you so much for listening. I'm happy to take questions.
Thank you very much, Dinithi, for this very clear presentation. We have a first question here from the audience by Lars, and online, please do not be shy to ask the question.
Hi, very nice work. Maybe I missed it, but how is the in indels time parameterized here? I didn't get that.
So if I understood the question, how was the time parameterized models were estimated? Is it?
No, and what kind of function is? I mean, I'm thinking about Thorne, Kishino, Felsenstein, their very elaborate time parameterized indel model, but there are also simpler versions. But I wonder which actual model you used.
I see. So I just described here. So we actually use this finite state machine, and where we have the insertions and deletions as two states, equivalent states, and then the insertions. If we go from a match state to an insertion state, that's like a gap open, and then if we extend the gaps, then we are going from insertion state to another insertion state. So all this can be used in terms of modeled using the probabilities associated. And then for the time parameterized version, what we did was we had under the Markov model that we have, we can estimate the optimal evolutionary time for each pair of proteins. So we binned the entire protein alignment data set into time bins. And then for each bin, we kind of computed optimal Dirichlet models that explain these tree-free parameters here. And then for each time bin, we have a different Dirichlet model estimation. And that was our kind of time parameterized version of the alignment model.
Okay, very good. Thank you.
Thank you very much for the question.
So I also have a question. Don't know if you're aware, but a few years ago there was some scientists who reported that there were some mistakes in the calculation of the blossom matrix, and they proposed a corrected blossom matrix. And then there was a follow-up work that claimed that the corrected matrix was performing less well than the original one. And so it would be very interesting to know, how the two compare with your measure? Is it something that you were aware of and that you might have tested by any chance?
Unfortunately, I didn't get to test it, but it's a very good suggestion that it's nice to see what would give as a total message length for the corrected version versus the the less corrected version. So it will be actually nice to see that comparison and see whether it agrees with the observations made. So that's a good suggestion. Thank you.
So, other questions? I think I've stimulated Ed here.
So one thing I was sort of curious about is, you started out by talking about this non-Markov behavior that's been observed before. And if we actually take the position that we don't have multiple multiple nucleotide substitutions, certain amino acid substitutions should be forbidden. And I was wondering, in your sort of improved matrices using this framework, if you thought about whether they implied essentially zero instantaneous rate for multi-nucleotide substitutions.
I see. So if I understood the question correctly, so you were saying about how we can go from the nucleotide substitutions to the amino acid substitutions, what the link is between in terms of the rates associated. Was it what?
Yeah, essentially, I mean, think about the structure of the genetic code, and I'm gonna hopefully not screw it up in my head, but for example, a tryptophan cannot change to a tyrosine without a minimum of 2 substitutions. So if we take the position that most substitutions at the nucleotide level are single nucleotide substitutions, the instantaneous rate between those amino acids should be 0. And in most of the old matrices, that's not true. And I'm wondering if you thought about your matrices in that framework.
I see. So in the work, I actually didn't think along the nucleotide level because we were sort of focusing on the amino acid level at that point. But it's a good direction to actually look at and see, and also how to model these instantaneous rates under like a continuous time Markov model context. But at the moment, I really have not much of insights in that regard because I haven't really done some studies on that level. But thank you very much. I think that will be a good direction to look at when actually optimizing a Markov model, whether to have the codon level substitution models for Markov behavior rather than the amino acid level. So I guess that's a good direction.